Now we're going to look at stoichiometry in reactions that involve gases. If you look at this particular example here, we want to know the volume of oxygen gas, we know the pressure, we know the temperature of oxygen gas. The only thing we're missing in order to find the volume would be the moles. What we're given is the mass of KClO3, which is a solid. So what we're going to have to do first is a stoichiometry problem. We're going to take the 22.2 grams of that solid, and we need to convert that to oxygen, which is the gas. So we're going to do grams to moles, stoichiometry, 123 grams per mole of the KClO3, and then we're going to do a mole to mole ratio. We want to go to oxygen. There are 3 moles of oxygen for every 2 moles of the KClO3 from my balanced chemical equation, 3 to 2. So first and foremost, it's a stoichiometry problem. This is going to get us the moles of oxygen, 0.271. Now we have our gas. That number we can use in the gas laws. We want to find the volume of oxygen, so we're going to take volume equals just the ideal gas law, nRT over P. Now we have the moles of the gas, 0.271. We know R, 0.0821 liters, atmospheres, mole Kelvin. Temperature, 26 degrees Celsius. Put that into Kelvin, 299. Divided by the pressure. Now the pressure is 735 millimeters. Divided by 760 to get us into atmospheres. So 0.967 atmospheres. So first and foremost, this is a stoichiometry problem. After the stoichiometry, we have an ideal gas law. 6.88 liters of oxygen gas. Sometimes gases are collected over water, and in such cases, part of the gas pressure is water vapor pressure. Let's look at this example. We have a solid, in this case, silver oxide, which is heated. Heating decomposes that solid, acts as a catalyst. So silver oxide is decomposed. It releases a gas. That gas is bubbled through water. So here's my water tank. The gas is bubbled through the water into the collection bottle up here. Well, the gas that's collected up here in this bottle is a mixture of oxygen and water vapor. So the main correction with this problem is we have to determine the pressure of oxygen. And you'll notice I've given you the vapor pressure of water is 21.1 millimeters of mercury. So the main correction we have to do if something is collected over water, we have to take the total pressure, which in this case was 751 millimeters, and we have to subtract the vapor pressure for water, which I told you was 21.1. We'll just round it 21. So the pressure of the oxygen, that's what I want, is 730. When you convert that to atmospheres, you divide by 760, because we're going to use the ideal gas law, 0.961. There's the really only correction that you have to make when something is collected over water. Okay, the first thing we're going to find is the moles of oxygen. So we're going to do the ideal gas law, PV, divided by RT. Pressure we just found, 0.961. That's the corrected pressure after subtracting the vapor pressure for water. Volume, we were told, is 0.0812 liters. R, 0.0821. Those numbers are kind of confusing there. 0.0821 liters, atmospheres, mole Kelvin. And the temperature we had was 296 Kelvin. So this is going to give me the moles of oxygen, 0.00321. We weren't asked for the moles of oxygen, we were asked for the grams of silver oxide. But now that we have oxygen and we have a balanced chemical equation, we can do some stoichiometry here. So take the 0.00321 moles, do your mole to mole ratio based on the chemical equation. It's 1 mole of oxygen for every 2 moles silver oxide. And then if I want to go to grams, add one more step there. In 1 mole, there are 232 grams of silver oxide. You'll notice this in the previous problem, they just kind of worked differently. In this one, I did the gas law first and then stoichiometry, instead of stoichiometry first and then the gas law. So I'd end up with 1.49 grams of silver oxide. But again, main correction, if something is collected over water, just subtract the vapor pressure for water. Dalton's law. The oxygen collected over water gives a mixture of gases, that is O2 and water. John Dalton considered that in a mixture of gases, each gas exerts a partial pressure that's independent of the presence of other gases. So here's kind of the derivation of Dalton's law. In total, which is a total number of moles, is equal to the moles of gas A plus the moles of gas B, so forth. Well, we can kind of get moles from the ideal gas law. So I'm going to substitute in here volume, RT, pressure instead of moles. So by making the appropriate substitutions with the ideal gas law, here's what Dalton's law really says. The total pressure of a mixture of gases is equal to the partial pressure of gas A plus the partial pressure of gas B, so forth. So let's look at an example that would incorporate Dalton's law. What's the partial pressure of H2 in a mixture that contains hydrogen and helium? We're given the volume, we're given the temperature, and we're given the total gas pressure. Now there's a couple ways to work this problem, but I'm going to do it using mole fractions. So I'm going to find the partial pressure of H2. Use the ideal gas law, nRT over V. So we're going to use N, which for hydrogen is 0.05. R is at 0.0821. Temperature is 293. And the volume is 5. So the pressure of hydrogen, the partial pressure of hydrogen, is 0.24 atmospheres. That's one way to solve this problem. Now there's a second way to solve this problem by using mole fractions. I can find the mole fraction of hydrogen by taking the moles of hydrogen, which is 0.05, divided by the total number of moles, which is, there's only two gases, 0.05 plus 0.125. Now the mole fraction doesn't have any units, it's just a number, it's basically a percentage, but it's going to be 0.29. So hydrogen occupies 29% of this mixture of gases, basically. If I want to find the partial pressure of hydrogen, I can simply take the mole fraction of hydrogen multiplied by the total pressure. So we're going to take 0.29. I was given the total pressure in the problem, 0.84 atmospheres. So hydrogen is 29%, basically a 0.84 atmospheres. The partial pressure, or the pressure of hydrogen, is 0.24 in that mixture of gases. So there's a couple ways to solve it, but you are more than likely going to have to use the mole fraction way. I gave you enough information here to use the ideal gas law, but you need to know how to set up a mole fraction.